So
All
today
right. Oh,
we
sorry.
have, I'll introduce you. That's nicer. So today we have Carissa Slone talking about characterizing two slices over C2 and K4.
All right. Thank you, Sarah, for organizing this and for the introduction. And thank you all for coming today. All right. Today we're talking about the slice filtration, which was developed by Hill Hopkins and Ravenel in their solution to the Curvaire invariant 1 problem. So what it does is that it decomposes genuine G spectra into irreducibles, which we call slices. And we know a couple things about the slice filtration. For example, we know the 1, 0, and -1 slices over some general group G, where G is finite. And throughout G is going to be a finite group. And today we're going to talk about two slices over C2 and Klein 4, which I'll mostly write as K, which is C2 crossed with C2. First up, we've got some necessary background. Sigma is the one-dimensional sign representation of C2. What we have is a copy of R, which I'll call R sigma. And what sigma does is that it acts by flipping. And then the regular representation of C2 is rho C2, which is 1 plus sigma, where 1 is the trivial representation of C2. And then S sigma is the 1-point compactification of R sigma. We're talking about Klein 4, so we also want to know about the representations of Klein 4, and it has 3 sign representations, and they're the pullbacks P1 star sigma, M star sigma, and P2 star sigma, where P1, M, and P2 are these maps from Klein 4. We can project onto the first factor, apply the multiplication map, or project onto the second factor to get to C2. And then from C2, we can get to R via sigma. And then the regular representation of Klein 4 is rho K, which is 1 plus P1 star sigma plus M star sigma plus P2 star sigma. We're talking about genuine G spectra. So of course we want to talk about their homotopy, and the homotopy of a genuine G spectrum takes the form of a Mackey functor, which we denote with we're going to call it M underline, and all Mackey functors are going to be underlined. And such a Mackey functor M for a finite abelian group G is going to be abelian groups M of G mod H, which I will denote with M sub H. And that's for every subgroup H of G. And for all K contained in H, we're going to have maps. At the top is M sub H. At the bottom is M sub K. Maps going down are called restrictions. Maps going up are called transfers. And they satisfy the double coset formula. And each level has a Weil group action. We're going to represent them pictorially with Lewis diagrams, which is what I've drawn here. Let's get some examples. For C2, we have a C2 mod C2 at the top and a C2 mod E at the bottom. And we have 4 C2 Mackey functors we want to think about today. The first step is the constant Mackey functor Z with a Z at the top and a Z at the bottom. The restriction is the identity, and the transfer is multiplication by 2. And we call it a constant Mackey functor because all of the Weil group actions are trivial. We can dualize our Mackey functor to get Z dual, where how we dualize Mackey functors is that we leave the groups alone and we just swap the restrictions and transfers. So now our restriction is multiplication by 2 and the transfer is the identity. Next up is G, which is a copy of F2 at the top and a 0 at the bottom. So of course the restrictions and transfer is 0, in which case I'm not going to write them. And then if we swap that 0 and F2, I'm going to call that Mackey functor F. For Klein 4, the diagram gets a little bit more complicated. We have a K mod K at the top, a K mod L, K mod D, and K mod R in the middle, where L, D, and R are the left diagonal and right subgroups of Klein 4, respectively. And then we have a K mod E at the bottom. We also have the constant Mackey functor Z, where the restriction is the identity and all of the transfers are multiplication by 2. We have the dual to the constant Mackey functor Z, where now, again, the restriction is multiplication by 2 and the transfer is the identity. And we can combine these two Mackey functors to get what I call Z2-1 dual, where at the bottom it looks like Z dual, and at the top it looks like Z. Next up, I call this Mackey functor M because it looks like an M, and we have F2 in the 4 upper spots and a 0 at the bottom. And our non-trivial restrictions are the identity. We also have a version of G for Klein 4, which again is an F2 at the top and zeros everywhere else. And then the Klein 4 version of F is an F2 at the bottom and zeros everywhere else. Another important construction with Mackey functors are those of pullbacks. Given some surjection phi n from G to G mod n, where the kernel is n a normal subgroup of G, we have a pullback for Mackey functors. Phi star n from G mod n Mackey functors to G Mackey functors, defined by phi star n of M of H is M of H mod n, if n is a subgroup of H, and 0 otherwise. For example, phi star C2 of F2, well, that's an F2 at the top and a 0 at the bottom, which is our Mackey functor G. Phi star K of F2 is an F2 at the top and zeros everywhere else, which is again our Mackey functor G. And then if we pull back Z over L, well, we're going to have a copy of Z concentrated over L. And zeros everywhere else. One thing that is of particular interest with the slice filtration is slices of Eilenberg-MacLane spectra. In an Eilenberg-MacLane spectrum, HGM has homotopy Mackey functors. Pi n is m in degree 0 and 0 everywhere else. So just like an Eilenberg-MacLane space, except now it's a spectrum. For example, we have HC2Z, HC2G, HKM, HKF, any of the Mackey functors that we've seen already. Now we're ready for our theorems and definitions. We're going to let tau at least NG, contained in the category of genuine G spectra, be the localizing subcategory generated by G spectra of this form, where H is a subgroup of G, rho H is the regular representation of H, and K times the order of H is at least N. And we're going to write X at least N to mean that X is in tau at least NG. Now G spectra of this form, SK rho H is a representation sphere for H. Smashing with G over H induces that sphere up to G. And then we take the suspension spectrum. Now, a localizing subcategory is a full subcategory closed under a number of constructions, including cofibers and extensions. It's
sorry,
yes.
Does only work for positive n? What you wrote down here?
It is for any integer n. I mean, yeah, any integer n. So you can have negative and positive.
Mm-hmm. Okay.
It's important to note that a localizing subcategory is not closed under desuspension or fibers. For example, tau at least 0e is the category of connective spectra. Which is not closed under desuspension or fibers. Along with this localizing subcategory, we get a localization functor, P lower star, from genuine G spectra to tau at least star G. Natural maps from P lower n plus 1 to P lower n. And then we're going to have cofiber sequences from P lower n plus 1 of X to P upper n of X, where X is some genuine G spectrum. It's also important to note that Hill-Hopkins and Ravenel use the original slice filtration, but today we're working with the regular slice filtration from Ullmann. All of the results are the same except for an indexing difference of 1. Now we have this definition for X to be at least n, and we also have a definition for X to be less than n. And we're going to say that X is strictly less than n if the H equivariant maps from SK rho H plus R to X are 0 for all R at least 0, every subgroup H of G, and for all K such that K times the order of H is at least n, i.e. there are no maps from generators of tau at least NG. Now, if we have for some G spectrum X, both X at least n and X no bigger than n, then we call X an n slice. And that's what we're really concerned about finding with the slice filtration, these n slices. And how we're going to go about doing that is, well, take a spectrum, determine if it's at least n, determine if it's no bigger than n, and if so, we've found our n slice. Now we're ready for some propositions regarding the slice filtration. First up, we have this idea of a pullback of Mackey functors. Then it turns out we also have a pullback for G spectra. So we're going to take some surjection Vn from G to G mod n, and we have a geometric pullback functor, phi star n, from G mod n spectra to G spectra. And phi star n of this representation sphere smashed with H G mod n of m is equivalent to SV smashed with HG V star n m, where V is some G representation and m is a G mod n Mackey functor. For example, phi star C2 of HF2, well, that's equivalent to HEF2, C2, phi star C2 of F2. But we already know that phi star C2 of F2 is G. And for Klein 4, phi star L of H C2Z is equivalent to HK phi star L of Z. We have this really great result regarding pullbacks, and this one is due to Hill and Ullman. We're going to take N to be a normal subgroup of G, and if the G mod N spectrum X is a K slice over G mod N, then the pullback phi star N of X is a K times the index of N and G slice over G. This is really useful because it's easier to find slices for smaller groups. So if we know the slices, if a spectrum is a slice for some subgroup of G, then we can pull back that slice to G to get another slice, a slice for our bigger group, which is, again, really useful because it's easier to find slices for smaller groups. So this is a way that we can determine whether a spectrum is a slice is by, well, we can look at the smaller group and what's going on there and then pull back that information. Another really useful computational tool is due to Hill, Hopkins, and Ravenel. And we're going to take any integer k, and the k plus order G slice of the row suspension of X is equivalent to the row suspension of the K slice of X, i.e., the slice filtration commutes with suspension by the regular representation. So if we have some slice, if we suspend it by row n number of times, well, we're going to get another slice. Earlier, I promised you the 1, 0, and -1 slices, and now we're ready for those. We're going to take some G spectrum X from Hill, Hopkins, and Ravenel. X is going to be a 0 slice, if and only if it's equivalent to an HGM for some Mackey functor M. Putting this in terms of homotopy, pi 0 of X is M, any Mackey functor you want, and then pi n of X is 0 when n is not 0. Also due to Hill, Hopkins, and Ravenel, X is a 1 slice, if and only if X is equivalent to a 1-fold suspension of an HGM. But now our Mackey functor has to have injective restrictions. So pi 1 of X is M, where M has injective restrictions. and pi n of x is 0 if n is not equal to 1. And finally, the -1 slices are due to Ullmann. X is going to be a -1 slice if and only if x is equivalent to the one-fold d-suspension of an HGM. But now our Mackey functor M has to have surjective transfers. Again, in terms of homotopy, pi -1 of x is M, where we have surjective transfers, and pi n of x is 0 when n is not equal to -1. For example, these last few propositions, HC2G is a 0 slice. The one-fold suspension of HC2G, well, that's equivalent to the pullback over C2 of the one-fold suspension of HEF2. That's a 2 slice. Here we have a non-equivariant spectrum. So it's a 1 slice. And then because the index of any in C2 is 2, 1 times 2 is 2. So we have a 2 slice. The row suspension of HC2Z is a 2 slice because the order of C2 is 2 and HC2Z is a 0 slice. The 1 plus row K suspension of HKZ21 dual is a 5 slice because Z21 dual has injective restrictions and the order of Klein 4 is 4. And finally, the -1 minus 2 row K suspension of HKZ dual is a -9 slice because Z dual has surjective transfers in the order of Klein 4 is 4. These last two propositions characterize all slices over C2 because every integer is congruent to 0 or 1 mod 2. For Klein 4, on the other hand, we're missing the 4K plus 2 slices, which is why we want to talk about them. We're now ready for our results. First up is C2, and we're talking about C2 because all of the information for Klein 4 has to restrict to the appropriate information for C2, which is why we want to start there. Proposition A, a C2 spectrum Y is going to be a 2 slice if and only if its only non-trivial homotopy is pi 1 of y and pi 2 of y, where we have some conditions. The restriction map in our pi 2 has to be injective, and the group at the bottom of our pi 1 has to be 0. And turns out that means that both the one-fold suspension of our pi 1 and the two-fold suspension of our pi 2 are both 2 slices. I'm going to forgo most proof sketches in favor of examples. We will have a proof sketch at the end, but for right now, we're going to focus on examples. All right, let's take a look at those. The one-fold suspension of HC2G is a 2 slice because our group at the bottom of G is 0. Another way we can see that is that we already saw that we have a pullback. So we have a 2 slice. So there is more than one way to see that a spectrum is a slice. We've got all of these great computational tools. So if we're having trouble with one method, well, then maybe a different method is going to work. On the other hand, the two-fold suspension of HC2G is not a 2 slice. Our restriction is not injective. Another way to see that it's not a 2 slice is that we have a pullback. So we have a 4 slice, which then means that it has trivial 2 slice. The two-fold suspension of HC2Z dual is a 2 slice because Z dual has an injective restriction. And finally, the row suspension of HZ is a 2 slice. Our pi 1 is G, and our pi 2 is F. And here our group at the bottom of our pi 1 is 0, and F has an injective restriction. And we already saw this in our previous example. We have a row suspension. So we have a 2 slice. Again, there's more than one way to see that a spectrum is a slice. That's the story for C2. Now we're ready for the story for Klein 4. Proposition B, the K spectrum, the one-fold suspension of HKN is a 2 slice if and only if NE is 0. The group at the bottom of our Mackey functor is 0. And the map NK to NL plus ND plus NR via the sum of the restrictions, the upper restrictions. This map needs to be injective. For example, the one-fold suspension of HKM is a 2 slice. And let's remind ourselves what M was. M was a copy of F2 in the 4 upper spots, and a 0 at the bottom. And our 3 non-trivial restrictions are the identity. All right, so ME is 0, and the map F2 to 3 copies of F2 via the sum of the identity. That map is injective. the one-fold suspension of H phi star L of Z is a two slice. And let's remind ourselves what phi star L of Z is. It was a copy of Z concentrated over L. And zeros everywhere else. All right, our group at the bottom is 0. And the map Z to Z plus 0 plus 0 via 1 plus 0 plus 0. That map is injective. So that's the one-fold suspension of some Eilenberg-McQuain spectrum. Now we're going to take a look at the two-fold suspensions. The K spectrum two-fold suspension of H M is a two slice. If and only if all restrictions of M are injective, and the sequence MK to ML plus MD plus MR via the sum of the upper restrictions, and then from ML plus MD plus MR to M, 3 copies of ME via this matrix involving the lower restrictions. This sequence needs to be exact. For example, the two-fold suspension of H Z and the two-fold suspension of H Z21 dual are two slices. Both of these Mackey functors have injective restrictions. Let's take a look at that sequence for a Z21 dual. All right, we're mapping from Z to 3 copies of Z to another 3 copies of Z. On the left, we have the sum of the identity. And on the right, we have a matrix with a bunch of 2s. The kernel of this matrix is the diagonal subgroup of our groups in the middle. All right, let's take an element of this kernel. Well, there's an integer that maps to this element, so our sequence is exact. On the other hand, the two-fold suspension of HZ dual is not a two slice. It fails the exactness condition. Let's take a look at why. All right, now our map on the left is multiplication by 2. And let's take the elements 1, 1, 1 in our kernel. Well, there is no integer that maps by multiplication by 2 to 1, so our sequence is not exact. Now this is interesting because remember the two-fold suspension of H C2Z dual is a two slice. This is an example of how it gets harder with bigger groups to determine what spectra, if a spectrum is a slice. It was really easy for the twofold suspension of HZ dual to be a 2-slice for C2, because all we needed was for the one restriction to be injective. But now when we move up to Klein 4, we have 6 restrictions. All of those have to be injective. And we have this exactness condition that it fails. So it's a lot harder to be a 2-slice for Klein 4 than it is for C2. Now, a natural question to ask is then, what is the 2-slice of the spectrum? We're going to start with a short exact sequence of Mackey functors, Z dual to Z21 dual to G. And how we map between Mackey functors is level-wise. All of the possible squares have to commute. And what this short exact sequence gives us is a cofiber sequence. The one-fold suspension of HG mapping to the two-fold suspension of HZ dual, mapping to the two-fold suspension of HZ21 dual. All right, here we have a 4-slice because it's a pullback. And the index of E in K is 4. And we just saw that this spectrum is a 2-slice. So we have a cofiber sequence. It starts with the slice, it ends with the slice, and our desired spectrum is in the middle. Therefore, we've found the entire tower for the two-fold suspension of HZ dual. What we need is cofiber sequences stuck together so that they end with slices and start with slices, which is what we found. And if it looks like the tower, it is the tower. If it looks like a slice, it is a slice. Those are the slogans. All right, so we found everything we need to know. So now we can see that the two-fold suspension of HZ dual, its 2-slice is the two-fold suspension of HZ21 dual. And finally, if we take the two-fold suspension of HG, we'll remember that is the pullback over Klein 4 of the two-fold suspension of HEF2. That's not a 2-slice because it fails the injective restrictions condition. And again, we can see that because we have this pullback, or we can see it's not a 2-slice because it's a pullback. So it's an 8-slice. Therefore, it has trivial 2-slice. Now we're ready for the theorem. We're going to suppose that the K spectrum X has only the non-trivial homotopy. Pi 1 of X and pi 2 of X, where pi 1 of X satisfies proposition B, and pi 2 of X satisfies proposition C. Then X is a 2-slice. Conversely,
Sorry, would you mind saying what the two propositions were again? Sorry.
yeah, so proposition B, let's scroll back to it, had to do with the one-fold suspension of some spectrum, and that was a 2-slice if and only if a group at the bottom of our Mackey functor was 0, and we had this injective map. So we're talking about one-fold suspension of the pi1 of X. And then proposition C, we're talking about the 2-fold suspension of our pi2 of X. And we need all of its restrictions to be injective, and we need this sequence to be exact. So if our spectrum X, it's only non-trivial homotopy, our pi1 and pi2, where one-fold suspension of pi1 is a 2-slice, and our 2-fold suspension of pi2 is a 2-slice, well then X is a 2-slice. On the other hand, if X is a 2-slice, then it turns out its only non-trivial homotopy is pi1 of X and pi2 of X. Where the 2-fold suspension of H pi2 of X is a 2-slice, and the one-fold suspension of H pi1 of X is in the interval 2 to 4, i.e. proposition C and part of proposition B hold. This is where we're going to have the proof sketch. The forward direction follows from propositions B and C. If X is a 2-slice, turns out that means its only non-trivial homotopy is pi1 of X and pi2 of X. Which then means that we have a fiber sequence. And 2-fold suspension of H pi2 of X, mapping to X, mapping to the 1-fold suspension of H pi1 of X. Our 2 spectra on the left are both at least 2. Therefore, our spectrum on the right is at least 2. From the definition of strictly less than 5, we find that the 1-fold suspension of our pi1 of X is less than or equal to 4. And then finally, we're going to rotate our fiber sequence to get our H pi1 of X mapping to our 2-fold suspension of H pi2 of X mapping to X. On the left, we have a 0-slice. On the right, we have a 2-slice. Therefore, our spectrum in the middle is in the interval 0 to 2, i.e. it's less than or equal to 2. And because we already know it's at least 2, we know we have a 2 slice. Now, I said that only part of proposition B has to hold. And the part that doesn't have to hold is that this map doesn't have to be injective. For example, we're going to take X to be the 1 plus P2 star sigma suspension of HE, where E is this Mackey functor, and F2 at the top, a 0 and 2 F2s in the middle, and an F2 at the bottom. And we have 2 non-trivial restrictions, which are the identity, and 2 non-trivial transfers, which are the identity. Then X is a 2 slice. And it has pi 1 equal to G, and pi 2 equal to F. All right, so pi 2 of X satisfies proposition C. And our pi 1, well, it fails the injectivity condition. We map from the top F2 to 3 copies of 0 via the 0 map. That map is not injective. So this injective map condition doesn't have to hold. And that is all I have for you today. And thank you again for having me.
Yes, on behalf of everyone, I'd like to thank Carissa. Are there any questions?
Hi, Carissa.
Yeah.
Thanks for your talk. Is the ROK4 graded homotopy group of HZ completely known?
Yeah, I calculated that in determining.
I know there is a paper by Holler and Krish, but they only computed the Poincare series of them.
Yeah, so I actually computed the slices of HKZ for any integral suspension, which then that actually gives you all ROK graded homotopy.
For HF2.
Oh, for HF2, yeah, HF2 that would be Guillou Yarnall. They have part of it. They calculated. Actually, no, they have all of it. They calculated the slices of the integral positive suspensions of HF2, which then gives you all ROK graded homotopy.
What about HZ?
HZ?
Yes.
So that would be.
Okay.
Yeah.
Okay, thank you very much.
I have a different question.
Yeah.
Does the slice filtration correspond to a T structure, or is it something more subtle?
I am not familiar with the T structure.
As in, you have 2 sequences of subcategories. So for each index, a greater than or equal n and a smaller than or equal n subcategory. And they have to, there are 3 axioms that mapping from the greater than or equal n down to the n minus 1, the mapping space is all trivial. They have to be, one of them is closed in a suspension, the other one is closed in a loop space. And the last one is that you always have those fiber sequences. The ones that you also had, where you, for an arbitrary object, you can sort of decompose it in one that is greater than or equal n, and the co-fiber is then smaller than or equal n minus 1.
Okay, yeah, no, that sounds a lot like this. I can't say for sure, but that'd be an interesting thing to look into to see if they are correlated.
Because there is a T structure on an equivariance spectrum, which is just given by homotopy groups. So then the homotopy groups would sort of vary with subgroups and give Mackey functors.
Yeah, yeah.
And that's exactly the standard sort of T structure that I know. And it looks so similar, yet I'm not sure if it is.
Yeah, I cannot say for sure, but that does sound like an interesting thing to look into.
All right.
Yeah, I believe there is a reference for that somewhere. I'm not remembering what it is right now, but I'm pretty sure it does exist.
Okay.
T structures and slices. I was curious about what the motivation for Proposition C was.
Yeah, Proposition C. So wanting to know about the twofold suspensions?
Yeah.
Yeah, so this came out of a lot of examples and calculations where it seemed like the only kinds of two slices you got were the one-fold suspensions and the two-fold suspensions. And that led to saying, okay, well, can we characterize like what makes these slices? And also another reason to think about the two-fold suspensions for Klein 4. Well, we can really easily find out what the two slices for C2 are, and those are one-fold suspensions and two-fold suspensions. So we want to also look at two-fold suspensions for Klein 4.
Okay, that makes some sense. Are there other questions for Carissa?
Maybe kind of a vague one, but like, do these computations sort of get intractable quickly? Like if you start taking larger groups or larger orders of groups?
Yeah, it gets pretty difficult pretty quickly. And part of that is because of like the Mackey functors get really big. For example, like with Klein 4, it was really easy for the two-fold suspension of HC dual to be a two slice. But as soon as we added in one more level to our Mackey functor, we upped the order of our group just by 2, then this condition to be a two slice got a lot more difficult. Yeah, the calculations get a lot more difficult the bigger the groups get.
Do you expect like an analog of this proposition C to be true for other groups, like some kind of matrix thing or some kind of exact sequence to hold?
Yeah, so actually the next group I'm thinking about is the quaternions. And so the quaternions restrict to C4, and you can pull back Klein 4 to the quaternions. So I'm really interested in how the two slice characterization changes. And I would expect to be some sort of correlation just because I can pull back that information for Klein 4. And I'm really interested to see how it changes.
Yeah, the quaternions are great.
Yeah, I'm excited to be working with them next.
Well, if there are no more questions, I'd like to thank Carissa again.